I don't have a very long talk prepared, so I'll try to go slow and feel free to interrupt at any point with questions. So let me also first acknowledge co-authors Tudor, who's here, who gave a wonderful talk earlier in this workshop, who you all know. Everything will be joint work with Tudor, Larry, and John, who's one of the organizers of the workshop. Okay, so let me get started. So one slide of very broad motivation about what it is that we're trying to do and why. The optimal transport framework, everyone here is, of course, very familiar. It yields some set of tools, which are distances and maps between distributions that are useful in data analysis. There's been a lot of renewed interest recently, both in statistics and machine learning, in a lot of adjacent communities for various reasons. And maybe arguably in scientific applications, one thing that we need is some slightly better understanding of statistical aspects. So statistical aspects here means how well can we estimate various things. So how well can we estimate the distances and maps that arise in this OT framework, and maybe going a little bit further, answering questions beyond how well can you estimate things, how well can you quantify your uncertainty. So what is the variability in these estimates? So these are maybe predominantly or classically understood as statistical questions that center around optimal transport. And so this is maybe the focus of today's talk. I'll tell you a little bit about some questions in this space. And maybe at a very high level, what excites me about this area is just the interdisciplinarity of it. So somehow tackling all of these seemingly basic statistical challenges seems to require a lot of understanding of tools from PDEs, from convex analysis. It intersects a lot of interesting areas that are all new for me. Okay, let me just begin by telling you what the setting that we'll start off with is today. So we'll be talking about the statistical estimation of optimal transport maps. So let me be pretty formal pretty quickly. So here's the setting you should imagine. You're going to observe n samples drawn from a distribution P and n samples drawn from another distribution Q. And we'll make an assumption here. And the assumption, I will tell you a little bit more about this regularity condition in a minute. But the condition is going to be that there's some smooth and strongly convex function phi0. And this function links Q to P in the following way. The gradient of this smooth and strongly convex function pushes P onto Q, right? And we'll call T0, which is the gradient. This will be the optimal transport map for the quadratic cost between these two distributions. So it is the OT map that maps P onto Q. Everyone okay so far? So the setting is that you have a smooth and strongly convex function whose gradient pushes P onto Q. And you're, instead of giving access directly to the distributions, what we'll give you access to is samples from the two distributions. And what is the goal? The goal is going to be to estimate T0, right? So you don't have access to the distributions P and Q, and you'd like to construct an estimate which is accurate in some sense. And so here's the sense in which we'll care about its accuracy. We'll care about its L2P error. So that is, we'll measure how far is T hat from this unknown map T0 as measured in this way. Look at the integral of the squared distance between T hat and T0. It's taken according to the measure P. And then we'll take an expectation over the randomness of the samples. So the samples X and Y are random. T hat is some function of these samples X1 through Xn and Y1 through Yn, and we'll take an expectation over these. So the goal for us will just be to construct an estimate T hat, which has small risk. So this is the risk that we will care about. Is everyone okay so far? Okay, great. And maybe more broadly, this is one of the basic questions in the field of statistical optimal transport. So statistical optimal transport maybe focuses on questions of estimation and inference for objects which arise in the OT framework, so things like the transport map, when you have samples from the distribution, so you have sample access to the underlying distributions. Okay, good. So let's keep going. So maybe the first question that one should ask is, okay, what are reasonable estimators for the transport map? And I'll tell you about two of them, and then I'll tell you a little bit about how one tries to understand their statistical properties. Okay, so maybe the first way to do this is, Jason already told you how you can compute. So if I give you samples, one thing that you can certainly do is either by Sinkhorn or some other method, by the Hungarian algorithm, try to compute the optimal matching between the samples. So let's say I give you n x samples and n y samples. You can compute the minimum cost matching between them. That itself doesn't give you an estimator of the transport map because you have to say something about what do you do outside of the support of the X distribution, right? So the minimum cost matching will give you some matching between the samples on the left and right. But in order to construct a transport map estimate that has small risk potentially, you care about what it does outside the support of the samples, but within the support of the distribution P. And so you have to give me some way to extend the matching outside of its support. And so one natural way is to use the nearest neighbors principle. So the nearest neighbors principle just says, if I give you a new sample point and you want to say where does it go, you just say, I'll pick the nearest neighbor in the X sample and go wherever the matching tells me to go. Right? So this is a potential extension of the transport map, which is defined on the sample. You extend it out of the sample using the nearest neighbor principle. And so we'll call this the one nearest neighbor transport map. Just a note, you can compute this. This is an actual easy to compute map. You can also try to compute it more efficiently using something like Synchron algorithm, but you might lose some statistical efficiency doing this. Okay, is everyone good so far? Okay, so
Shiva?
Yeah.
Is this different from the map that so first of all, t hat, if you solve this, will be a gradient of a max-affine function, right?
Yeah.
But then you can define the max-affine function everywhere, and then that would also give you a notion of Tn hat of x for every x. Is that not correct? Is what I'm trying to say?
Yeah.
And is that similar to this Tn hat nearest neighbor, or yeah? That's my question.
I think that is different. That is, you could have said, yeah, I think it's different. This one, maybe Tudor knows the answer, but I think we analyze something like the convex least squares, which I think is that estimator that you said. And I think this is a different estimator than that.
Would this be just like taking maximum over like a local affine function, like some?
Yeah, there's some Voronoi effect that happens here that doesn't happen for your estimator, I think. Yeah.
So an estimator for you is what it's something for which you have a model that you can evaluate pointwise. So you have some formula like max of affine functions, or is it something else?
An estimator for me is something that's defined as a function of the samples that I give you.
Pointwise, but it's not black box, right? You open the box, but what's inside?
I guess I'm not sure I understand. So you have to give me a function that it is defined for every x, let's say, in the support of the distribution P. And it should be something that is computable based on the samples that I gave you. Is that okay? So this is an example of an estimator. It took in as input the two sets of samples. It produces for me something that I can evaluate on the entire support of P by saying, take any point in the support of P, move it to one of the samples, and then it'll output something in the support potentially of Q. Okay. All right, so that is one way of doing this. The other way of maybe the drawback of using the nearest neighbors principle to try to construct a transport map estimate is that it doesn't exploit any smoothness of the underlying distribution. So there's a long history in statistics of solving what's called a density estimation task. And roughly the idea is that if these two distributions, P and Q, have a little bit more structure, they're smooth in some way, they're Holder with some amount of smoothness, then maybe your estimator should be able to exploit it and do a better job of estimating the underlying distributions. The nearest neighbor estimator doesn't have this property. It does not exploit smoothness in any nice way. And so a different way to construct estimators is to go via the route of density estimation. So you try to construct a good guess of these two underlying distributions, P and Q, and you define your guess for the transport map as whatever is the optimal transport map between P hat and Q hat. So you'll need to make some set of assumptions to say, this is a well-defined object, but let's say we make those assumptions, then this is a way of defining an estimator. So you first try to estimate the underlying densities P and Q. We know how to do this reasonably well in some ways that exploit the smoothness of those underlying distributions. And then you define the map as whatever it is the optimal transport map between your density estimates. So this is also an example of an estimator of the map. It only accesses things via these samples that you have. Is everyone okay with this? These things are a little bit more challenging to compute, but again, we'll focus mainly on statistical issues, but you should imagine that one can compute things like this by somehow resampling or discretizing the estimates p hat and q hat. So in your head, you should imagine I gave you some data, you smoothed it in some way to obtain density estimates. Those two density estimates will be these smooth objects. And what you will compute by some method, discretization or otherwise, you will take these p hat and q hat and compute a map, which is this one. In this case, it's just sort of saying where should the mass flow to optimally transport this distribution to this one. Okay, so this is an example of what in statistics we would call the plug-in principle. So if I want an estimate of the OT map between P and Q, a reasonable method to try to construct such a thing would be to first try to estimate P and Q and then plug it into something, which is this box that returns the optimal transport map for you. Okay, and maybe I'll just say, okay, these two estimators are very natural heuristics. These are maybe two of the first estimators that one might come up with. If I said, given samples, try to construct reasonable estimates for the OT map, these are arguably very natural. They have somehow proven a little bit difficult to analyze, and so I'll tell you a little bit about how people have gone about analyzing them. Everyone okay so far? Good. Okay, so let's just try at a high level to understand what it is that we want to accomplish. So the estimator in this setting is derived from some sort of plug-in estimator. So you should think of it as, in both cases, you constructed something which is like a density estimate p hat and q hat. You constructed the OT map between them. We'll call that t hat. And the target is the OT map between the underlying distributions. So the target is t0. This is the thing that I want to estimate. It's the OT map between p and q. And so our question is basically, okay, we would like to say somehow that these two things are close to each other. And maybe the hope should be that if p hat is close to p and q hat is close to q in some sense, then these two maps, t hat and t0, would be close. Right? So the hope is that we'd like to understand when is this statement true. So when is it the case that the optimal transport program, this optimization program, is stable to perturbations of its input arguments? So you can view this as some sort of optimization program that takes as input two distributions and returns to you a transport map. And maybe you would like to understand when is it the case that it's stable in some quantitative sense. Everyone okay so far? Okay, good. So, and let me remind you again, now we'll discuss this key regularity assumption that will grant this OT program some very remarkable stability. So this is the assumption that we'll make throughout the talk. It's that this Brenier potential is smooth and strongly convex. So if you haven't seen this before, it's just saying that the Brenier potential, which links these two distributions, we're going to assume that it satisfies some very strong regularity condition, and in particular, it satisfies a quadratic upper bound and a quadratic lower bound. So this is the assumption that we will make. And maybe you should contrast this a little bit with, for example, Alessio's talk, where he talked about trying to, when is it that you can conclude that the Brenier map satisfies conditions, regularity conditions like this, when you make some assumptions on the distribution P and Q. In contrast, we will just hypothesize that this is true directly. Okay, and again, this was maybe part of the content of Alessio's talk. He told you a result of Caffarelli's, which just says, if P and Q have densities that are bounded away from 0 and infinity, and they both are supported on nice domains, then you should imagine that it will indeed be the case that the Brenier potential will satisfy this pair of conditions. So this is one way of thinking about when this condition holds. And another case where we know, again, by a result of Caffarelli, that such a condition holds is when P and Q are both log smooth and strongly log concave. So if this is true, so if you have P and Q, the source and target are both strongly log concave, essentially, then it will be the case that the OT map between them will be the gradient of a smooth and strongly convex function. Okay, and maybe at some level you should think of this as somehow being a little bit disappointing. So one of the reasons why we like the optimal transport framework is that it gives you these tools that are not brittle to these kinds of assumptions. Usually one of the things that we like is that OT is well defined when P and Q have very discontinuous distributions on very discontinuous domains. Arguably, when you care about statistical properties, so when you want to estimate these things, you need more than just that these objects are well-defined. You need them to be stable in some sense. And so this is why when you want to do statistical estimation, you often need to assume a lot more. And this is one such assumption. Again, let me pause for a second if anyone has questions. Yeah.
Yes, can you have access to these properties of P and Q based on samples only? Because that's the input you have is samples. So do you know if it has a smooth density or log smooth concave, or can you be sure?
No, yeah, so maybe you're asking, are these assumptions testable from samples? And I think that's a hard question. You'll have to sort of formulate very precisely what is possible. If it's that it could be any distribution and you want to know if it's log smooth, then you have no hope because there can be some small artifacts.
So a lot of degrees of freedom maybe because you just have limited information. So you can build your model, right? That's what you said. One of these methods, you build a density.
Yeah.
So you just should find one which is as nice as this. The theory says, no?
Yeah. So we should be a bit careful. These are not assumptions that are going to be made on p hat and q hat. These are not assumptions made on the estimate. They are made on the ground truth in order to say that the estimate will approximate the ground truth well. So, and you don't have access to the ground truth distributions, and all you have access to are samples, and you may not be able to test things like this. Yeah. Good. Thank you. Other questions? Okay. So now let me tell you one of the main results. So this comes from a paper of Tudor and mine that's recent. So here's the statement. So the two distributions P and Q satisfy this Brenier regularity condition. This is the thing that I told you about before. That is, they are linked by the gradient of a smooth and strongly convex function. So that is the only assumption being made. And now you say for any p hat and q hat, I can give you any other p hat and q hat, they have an OT coupling pi hat. From this OT coupling pi hat, I can derive a transport map t hat. This is just the barycentric projection of this one. So you should think of the coupling itself may not define a map, but I can project it onto the space of maps. We'll call that map t hat. Right? So given p hat and q hat, I can always derive this barycentric projection object, which is a transport map t hat. And what this result says is that the distance between t hat and t0 on the support of p hat, or on average taking an expectation over x drawn from p hat, this quantity is upper bounded by the Wasserstein distance between p hat and p squared plus the Wasserstein distance between q hat and q squared. Okay, so this is a stability bound in the sense that it says that if p hat and p are close in the Wasserstein sense and q hat and q are close in the Wasserstein sense, then it is indeed the case that t hat and t0 are close as measured according to this loss function. Is everyone okay? So this is maybe saying that the only assumption that you need is this Brenier regularity condition. Under that condition, it is the case that the optimal transport program as an optimization program is stable to perturbations of the input in the Wasserstein sense.
So here, are you assuming anything about p hat, q hat? So they could be the empirical distributions.
Yes, exactly. And then, correct, they can be the empirical distributions. So the only thing is that then you will get some statement about the in-sample matching loss. Yeah.
Related to Cody's question, just to try to interpret this next fact. So if I think about P and Q being empirical things, and I want the right-hand side to be less than epsilon, what's the right scaling of how many samples?
I'll give you examples like this, but maybe you should think of this as looking like n to the minus 2 over d. On the stuff on the right looks like n to the minus 2 over d, and this is the in-sample matching loss, so whatever it is. And I'll give you examples like this in a minute.
So why it's the 1 over lambda and lambda here? Is it,
I've written it in this way for a reason that'll be clear in a minute. I will upper and lower bound some quantities, and this will be some natural lower bound, and this will be some natural upper bound. You can put it on the right if you want. So it's just, it'll be easier to explain the next thing. Thank you. Okay, so maybe let me recap. This stability bound applies with essentially no conditions on p hat and q hat, but again, there's no magic going on. There's very strong conditions on the map between p and q. Okay? And maybe from a statistical perspective, what is the key statistical implication of this fact? If you want to understand rates of estimating t hat and rates for estimating t0 in the L2 p hat sense, right? So that's what this quantity on the left-hand side is. Then all you need to do is understand how well are you solving the task of density estimation under the Wasserstein laws. So this is providing for you some very nice reduction. It is saying that if you want to understand transport map estimation, all you really need to understand is Wasserstein density estimation. Okay, and so let me also remind you that at some point, the actual risk that we care about is not the p hat risk, it's the L2p risk. And so if you really want to carry out this program fully, you'll also need to relate the L2p hat risk to the L2p risk. And we'll do that in some cases.
Shiva, to just make your claim precise, should you not want also a lower bound with the same quantity? Means it just seems that this is an upper bound.
Yeah, so I'm saying that if you want to upper bound this quantity, all you need to do is bound this thing.
Yeah, but I just want to understand the left-hand side. So it may not be the case. Means this could be smaller in some sense, right?
Yeah, and okay, so maybe, as far as we know, in all the examples we know, this is a sharp characterization. It may not be the case universally. It is almost certainly not the case that you can lower bound it always by this quantity. So in some minimax sense, it is true that these upper bounds are sharp, but in some pointwise sense, I don't necessarily think it will always be a lower bound. Good. Okay, and let me remark again that qualitative stability bounds, which are things that roughly say if p hat converges to p weakly, then t hat converges to t0, things like this have been known for a very long time. And quantitative stability bounds are also not new. They are many variants of statements like this have been known. Promit and Bodhi have a paper that derives stability bounds that maybe roughly look like this. Hutter and Rigolet maybe actually revitalize some of this. So this is Philippe Rigolet and Jan Christian Hutter, where they didn't derive stability bounds in this form, but they derived something else that implies some sort of dual version of bounds that look like this. So they derived something like dual growth conditions, which are useful for analyzing things. And again, there are many other papers that derive bounds that at least at some level look like this. Okay, questions so far? Good. So let me now walk through the proof of this. It's simple enough that I can tell you about it pretty fast. So the key quantity in determining stability, and this quantity appears in various forms in all of the previous papers, is the growth of the semidual functional. So if you write down the Kantorovich program and write down its dual, and you sort of partially optimize its dual, you will arrive at this functional which is minimized by the Brenier potential. So if I give you a pair of distributions, you can say, what is the expected value of, and I take some function phi, and I say, what is the expected value of phi under p plus the expected value of the conjugate under q? Right? So this is some functional that, given a pair of distributions and a function, it spits out some value, and it is a functional that's minimized at this Brenier potential of phi 0. And now you can ask, okay, how does this functional behave as I move away from the minimizer? And the strong convexity and smoothness of the optimizer of this thing will grant you some sort of quadratic growth of this functional around its minimizer. So as you move away from the minimizer, this functional grows in some nice way. And this is a helpful fact, and somehow underlies a lot of stability. So for us, maybe the key thing that will be useful is this other fact, which is if I looked at how this functional grows around its minimizer, it has an exact expression. It is, so if I looked at the semidual with p hat, q hat at the true Brenier potential phi 0 versus p hat, q hat at the minimizer, which is phi hat, if I looked at its growth, so this is a different one of these semidual functionals, I'm looking at how it grows around its minimizer. It'll turn out that this has an expression which is, it's exactly a Bregman divergence. It's an integrated Bregman divergence against this coupling pi hat. And it's measuring how far you should think of this maybe for now as t hat. And so it's saying something like, how far are t hat and t0 as measured by this Bregman divergence. And this Bregman divergence is the one that's induced by the conjugate phi 0 star. Okay, so there's this exact expression that one can derive. It's maybe not very hard to derive. And this expression will just be useful for us. And you can also ignore all of the connection to the semidual and just focus on this Bregman divergence. And what we'll do is just upper and lower bound this Bregman divergence. And this will give us a stability bound. Everyone okay so far? Okay, so maybe the first fact to notice is that, okay, let's suppose I just started with this Bregman divergence. The strong convexity of phi 0 star will immediately give you a lower bound. So we've assumed that phi 0 is smooth and strongly convex, which also implies the same assumption holds for phi 0 star. And the strong convexity of phi 0 star will immediately give you a lower bound on the Bregman divergence. In particular, it'll tell you that this Bregman divergence can be lower bounded by exactly this quantity over here, which is just how far are y and t0 of x, where x and y are drawn from this coupling pi hat. Right, so point-wise, you can lower bound this Bregman divergence by a quadratic. That's exactly what the curvature condition is telling you. You can point-wise lower bound this by y minus t0x squared, and then you take an average with respect to pi hat. Everyone okay so far? This is maybe nothing interesting. I'm just saying this Bregman divergence can be lower bounded by this quadratic quantity. You can now apply Jensen's inequality, and it will immediately give you the claim that the barycentric projection, so if I sort of replace the y by t hat, it'll still be true, where t hat is this barycentric projection. So that is a lower bound on this difference between semidual functionals. Okay, and so maybe what is actually interesting about this stability bound is how does one get the upper bound? And I'll tell you about that now. So the upper bound is somehow, what you want to do is massage this Bregman divergence quantity to be in terms of these statistically meaningful quantities, which are these Wasserstein distances. And I will tell you how to prove the case where we'll assume that the source measure P is known, and the only thing I'm perturbing is Q. Right? So this is just a simpler version of the stability bound. Everyone tracking so far? So let's do this. So let's suppose I give you x and y. They're drawn from pi tilde. Pi tilde is going to be the OT coupling between P and Q hat. So what I promised you was that this difference of semidual functionals can be written as a Bregman divergence. Here's the Bregman divergence written out. It's just the expectation. This is the Bregman divergence with phi 0 star between y and t0 of x. Okay? The one fact that you need to know is that the gradient of phi 0 star sort of is the map that inverts t0. So that is grad phi 0 star of t0 of x is just x. Okay? So this Bregman divergence can be written as phi 0 star of y minus phi 0 star of t0 minus x times x transpose y minus t0 of x. Okay, and now we'll use a neat fact. So the neat fact is just that the OT coupling is optimal. What does it mean to be an optimal coupling between a pair of distributions? It just means that if I take any other z drawn, so the OT coupling has this property that it sort of maximizes correlations. So what does that mean? If I take any other z, which has the correct marginal distribution Q hat, it is the case that the expected value of x dot y, so x dot y are coupled by the OT coupling, has to be bigger than the expected value of x dot z, where z is any other thing with the same marginal distribution as y. Right? So the OT coupling maximizes correlation. So what I can do over here is look at this x dot y term and replace it by any other z that I like. So you should think of this as long as z has the same marginal distribution, this will give me a valid upper bound on this semidual difference. And now we will use the strong convexity of phi 0 or the smoothness of phi 0 star. And that will give me an upper bound on this in terms of the distance between z and t0 of x. And now I'm sort of free to pick the distribution of z. I'm free to pick z. All I need to respect is that its marginal distribution is Q hat. And so we will pick it to optimally couple t0 and z. So they have some marginal distribution Q and Q hat. You pick it from that optimal coupling, and so you will see that this quantity is just equal to the Wasserstein distance between Q and Q hat. Right? So maybe at a high level, what we've done is we've said you can look at this semidual difference and upper bound it by the Wasserstein distance, in particular by passing through some sort of suboptimal coupling in between. Okay, is everyone good so far? maybe let me return to the high-level takeaway. The high-level takeaway is just if phi0 is nice, smooth and strongly convex, then the ODE program is stable. It's stable to perturbations in the Wasserstein sense. Okay, so now let's talk about what are the useful statistical implications of this fact. Okay, so let me tell you about some results that we know how to prove now as a result of this. So there are 2 or 3 cases that have been studied in the past in the literature, so I'll tell you about those. So here's a case where you're trying to estimate the transport map, and what you're going to assume is that the transport map is alpha Holder. So here, this is the setting. It comes from Philippe Rigolet and Jan Christian Hutter. So this is the setting where I'm just going to hypothesize that the transport map is smooth, that I satisfy the Brenier regularity condition, and maybe that P and Q are compactly supported on some nice domain. So this is a simple test case. So what we're assuming, so this itself grants you the fact that the transport map is Lipschitz. What we're additionally assuming is somehow that the transport map is alpha Holder, where alpha is some number bigger than 1. Okay, so then what Hutter and Rigolet showed in this setting is that the minimax rate, so the performance of the best possible estimator, scales in some way. It scales as n to the minus 2 alpha over 2 alpha minus 1 plus d. If you're used to staring at non-parametric rates, if you were trying to estimate directly an alpha smooth object, the usual rate that you would expect would look like n to the minus 2 alpha over 2 alpha plus d. And so somehow this rate is a little bit faster. It's somehow easier to estimate an alpha smooth transport map than it is to estimate, say, an alpha smooth density. And this has some meaningful implication, which is at least if alpha is large enough, this can be smaller than a parametric rate. And so at some point, if you have enough smoothness, estimating the entire transport map is as hard as estimating a single average. So at some point, you will back into parametric rates. Yeah. Oh, just treating it as a constant. Not sure if I know the answer to this. Maybe I think it's just there's a lambda squared sitting in front. That's what will come from the stability bound. Okay, and maybe the only things to notice are that this is a non-parametric rate. So in contrast to, say, estimating an entropic map where you would get parametric rates, here you get something that decays pretty poorly with dimension. So estimating a high-dimensional transport map is hard. But it does also have this nice property that it exhibits some sort of elbow, which is if you have enough smoothness, you back into parametric rates. Okay, so this is a result that's known. And so what were we able to prove? So suppose that P and Q are alpha minus 1 smooth, and you have all of Hutter and Rigolet's conditions that hold. Then one thing that you can show is that the nearest neighbor map will achieve this rate n to the minus 2 over d. So this is somehow the natural scaling that you would expect when alpha is 1. And when alpha is bigger, the nearest neighbor map, as I told you, doesn't exploit smoothness in the right way. So when alpha is bigger than 1, you need to use something like a kernel or wavelet estimator. In that case, what we're saying is that, okay, as a consequence of the stability bound, somehow it will be the case that these plug-in estimators, which are somehow very natural, also attain minimax optimal rates. So, and I'll tell you a little bit about how we prove these things, but a consequence of the stability bound is just that these, if you're estimating a smooth transport map, the plug-in estimators that I described, which are the nearest neighbor estimators and these smooth estimators, they're in fact minimax optimal. Okay, so there are very closely related results that appear in Bodhi's work and also in other papers that, yeah, good. So questions so far about this result? Okay, so let me tell you the one interesting idea, which is how is this result proved? And this is how does one use stability in a sense? So maybe the question that one needs to answer in order to understand this is how well can we estimate a density under the Wasserstein laws? And how does this problem relate to more familiar density estimation problems? And so there's a nice result from Quentin and John Weed, which is just that if you have p hat and p, they have nicely upper and lower bounded densities, then it is the case that the Wasserstein distance can be written, the squared Wasserstein distance looks like an inverse Sobolev norm, right? So this is just a useful fact to know. So estimating something under the squared Wasserstein distance, at least if both p hat and p are nice, behaves like estimating P under an inverse Sobolev norm. And so this fact is just useful. So let me tell you what the inverse Sobolev norm is. So you're now trying to solve a density estimation task. I'm saying it's equivalent. The Wasserstein distance is equivalent to estimating this density in this inverse Sobolev norm. The inverse Sobolev norm, we all know what the usual Sobolev norm is. It just measures the h1 norm of a function, just measures the integral of the derivative of that function squared. The inverse Sobolev norm is the dual norm to this norm. So it is just a Sobolev IPM. So it measures the distance between p hat and p using test functions g, which are all Sobolev smooth. And so this is what the inverse Sobolev norm is. It's just an integral probability metric. It measures the distance between p hat and p as measured according to smooth test functions. And this maybe is one way of understanding why you get the rates that you get. So this is, as I pointed out, the rates for estimating a transport map are faster than usual non-parametric rates. And the reason for this is just that estimating the transport map is roughly equivalent to estimating the density under the Wasserstein loss. Estimating the density under the Wasserstein loss is like estimating a density not in the usual, say, L2 loss, but rather according to some smooth loss. And so this is why you get this alpha minus 1 upgrade in the rates. And so maybe just, yeah.
Shiva, isn't this very close to Wasserstein 1 also? Or?
Yeah, if you replace the Sobolev norm by the Lipschitz constant has to be 1, then it is exactly W1. Yeah, so this is very similar to the dual representation of W1. Great. And maybe the important point is it is not universally true. It is only true when you have these assumptions on the densities. They have to be lower bounded somehow. Okay, so what can we say beyond smoothness? This stability bound is sort of general and holds in some significant generality. So there are other implications that you can get. So here's one. Suppose that I tell you that P and Q are strongly log-concave and smooth, and I make no other assumptions. Then the nearest neighbor map already estimates consistently the transport map, and it estimates it at this rate, which looks like n to the minus 2 over d. Right? So this is just a consequence of the fact that when you assume that P and Q are strongly log-concave and smooth, then you know that the Brenier potential by a result of Caffarelli satisfies these Brenier regularity conditions that you need. And now you can apply the stability bound. And the stability bound will say, essentially, how well can you estimate these two densities in the Wasserstein sense? And the nearest neighbor estimator or the empirical plug-in estimator of these densities will already achieve this n to the minus 2 over d rate for estimating smooth and strongly log-concave distributions. So one nice implication is that just as a direct consequence of the stability bound, you don't have to require that the densities are smooth or anything like that. You can also estimate other transport maps between other classes of distributions. And here's another thing that you can do, which is, again, just sort of highlighting that the nearest neighbor analysis is actually very robust. It's just saying that suppose I give you two distributions that have 4 bounded moments, and you assume this Brenier regularity condition, then again, that's all you need in order to say that the nearest neighbor map is a consistent estimate and achieves this n to the minus 2 over d rate. Okay, so maybe at a high level, results for the nearest neighbor map, they follow from some well-known bounds on how well the empirical distribution estimates the population one under the Wasserstein distance, and this is somehow the right rate for those things. And once you have that, in order to analyze this nearest neighbor extension, all you need is some sort of Lipschitzness and some bounds on the diameters and probability contents of the Voronoi cells. These are somewhat easy to derive. And once you have these, you can just very quickly get results for the nearest neighbor map. So this is just highlighting the fact that the stability bounds are so general, somehow give you very quickly analyses, at least at this rate, for the nearest neighbor map. Questions about this? Okay, good. So let me change gears and tell you about a slightly different problem where, again, you can get some interesting insights just by looking at these stability bounds. So here's a different question. It's about estimating the Wasserstein distance itself. So the setting is going to be the same as before. We observe samples from P and Q, and we're going to assume that P and Q are linked by this strongly convex and smooth function phi0. And the question maybe that one might ask is, I don't care now about the transport map. What I care about is estimating the Wasserstein distance. So how far are P and Q according to the W2 squared distance? And maybe another statistical question that one might ask is, okay, can I construct a confidence interval for it? So can I construct some set that with high probability will catch this parameter that I don't know? Okay, and this is a nonlinear functional estimation problem. So what does that mean? I'm saying that in this setting, I don't care about the distributions P and Q. I don't care about the transport map. All I care about is a single number, which is what is the Wasserstein distance between P and Q. So there's this high-dimensional nuisance component that I don't care about. I don't care about the distributions P and Q. They might be hard to estimate. There's a single number that I care about. And maybe one question that one often wonders is it the case that I can estimate the single number at the parametric rate, at the rate 1/n, or is it much harder to estimate the Wasserstein distance? Okay. And so maybe a natural plug-in estimate is the Wasserstein distance between P hat and Q hat. Right, so there's a plug-in estimate of this, and one can ask, okay, how far are these two objects? And so here's a result from a paper of ours from a while back. It just says that if you have enough smoothness, so if alpha is at least d over 2 minus 1, and so if you have a fairly large amount of smoothness, then plug-in estimators based on these kernel or wavelet density estimators do in fact achieve the parametric rate. So that is, they are consistent at the rate 1/n as long as you have this amount of smoothness. And the other fact is that you can also characterize the limiting distribution. So you can say that root n times the plug-in estimate minus the truth has a normal distribution, and this allows you to construct a confidence interval in some straightforward way. Okay, so this is just saying that if you were interested in estimating the Wasserstein distance and the underlying distributions happen to be very, very smooth, then the plug-in estimator is consistent at the fastest possible rate, and you can understand the distribution of this plug-in estimator.
So with taking alpha greater than this, you kind of kill the bias term.
Yeah, exactly. So I'll explain this in a second, but yeah, that's right. So maybe one way of understanding this is that one of the object in our stability bound that we looked at was this difference of semidual functionals. This difference has a primal interpretation. So the semidual functional itself is just the Wasserstein distance up to some second moment quantities. And so when you expand it out, the difference between these two things looks like some sort of Wasserstein difference minus a linear correction. Right? So this is saying that the semidual difference is exactly equal to the difference between the squared Wasserstein distance between P hat and Q hat minus P and Q minus something which is some sort of, you should think about this as the first order Taylor expansion. So it's some sort of Taylor expansion of this quantity around this quantity. So once you know this, your stability bound from before will tell you that whatever this difference is, so the plug-in estimate minus the truth minus some linear correction is upper bounded by the squared Wasserstein distance. So this is just saying, you can say this is a Taylor expansion, or in this case it's called a von Mises expansion of the Wasserstein functional, and we're saying that the remainder, when I subtract off whatever this first order term is second order in this W2 topology. And so, as Pramit pointed out, all our assumptions are doing so. If you have enough smoothness, this quantity will be of smaller order than this first order correction, and you can essentially ignore it. So this is what we know by stability. And so what we can do is analyze this linear term. It's not quite this, but if this were some sort of empirical distribution, this would then be an average minus an expected value. When you have some additional smoothing, it's not quite that, but it behaves very similar. And so you should think of this as this is the term that contributes the central limit piece. It gives you a normal limiting distribution, provided that you can ignore this bias quantity. And this is exactly what happens when you have enough smoothness. You can ignore this and say that this thing will have a normal limit. Okay, and let me also point out that there is some sense in which CLTs for the Wasserstein distance have been known in far more generality for much longer. And so under much weaker conditions, so just say finite fourth moment, you don't need any smoothness, it is the case that the empirical Wasserstein distance does satisfy a CLT. You can think of this as the plug-in estimate of the Wasserstein distance, satisfies a CLT, but it's centered around its bias. So what this is saying is that if you ignore the bias, it is always the case that the variance is somehow of order 1/n. And so it's the case that if you were willing to take, somehow tolerate or use a CLT around this bias quantity, you have those CLTs hold in far more generality. And essentially what we are saying is that when you have enough smoothness, you can replace the centering by the true Wasserstein distance, and that is much more useful because then it's saying, okay, you're consistently estimating the true Wasserstein distance and not this bias object.
Shiva, but this CLT is not valid if P is equal to Q. Is that not right?
Yeah, that's right. This is away from the null, yeah.
But your result would be valid for P equal to Q?
It will also not be because of the same thing. It will degenerate for the same reason. This thing will have, this thing will have 1 over n behavior, not 1 over root n behavior. Yeah. Okay, so I'm about ready to stop. So let me just summarize quickly what we talked about. And so what we said for the part on estimating transport maps was just that under various smoothness conditions, natural transport map estimators are minimax optimal. This is the basic takeaway. And the key idea was that we developed these stability bounds that relate the plug-in transport map estimator's error to the error of density estimation in the W2 loss. And that latter quantity is far more familiar and easier to get a handle on. And then we talked about estimating the Wasserstein distance, and all we said was in some very high regularity regime, the plug-in estimator of the Wasserstein distance is asymptotically optimal and unbiased as an estimate for the Wasserstein distance. Okay, maybe as an outlook, okay, so I would argue that despite lots of work in the last several years, we've only started to scratch the surface of these statistical results for OT problems. There's a very basic question, which is at what rates can we solve transport map estimation when you don't make these strong curvature assumptions? You don't have these strong stability properties. What are the correct rates and what should one expect? Similarly, we don't have any real understanding of what are the minimax rates for estimating the Wasserstein distance. So we know that there are some regimes in which you can estimate them at the parametric rate, and that is optimal. But outside of that regime, we don't have a good understanding of what is possible and when. And maybe more broadly, there are many more problems about estimating barycenters, about estimating in the entropic setting, and there are many variants of OT. In all of these cases, we have very little understanding of the statistical aspects. And maybe the high-level takeaway is just that even though these OT tools are very robust, it seems like the inferential tools are still very brittle. Our understanding of when it is that we can get fast rates, can estimate these objects well, is sort of rudimentary still. So there's a lot of work to do still, and yeah, I'll stop here.